Hi everyone, this is Sohail and I'm going to talk about pragmatic learning-based congestion control for the internet, which is a collaboration with Chen Yu and Jonathan at NYU. Let's start from a key phrase on the title, learning-based. These days, people usually react to these kind of phrases in two completely different ways. In one group, we do have people who are very skeptical about the use of learning-based techniques in the context of network. On the other side of the aisle, we do have people who are very excited about that. But interestingly, both of these groups have their own good reasons why they believe in what they believe. Here we will look into these two questions, and with that, we will set up the key motivations of our work, and later we'll talk about the key decisions that we made. So first, let's start with why doing congestion control is important. Actually, the importance of congestion control comes from the fact that it directly impacts the quality of experience for different users in a network. In other words, the throughput that different users can achieve or the delay that they will experience in a network highly relate to the congestion control that they use. But to see why using lighting-based approaches can be, of great help in this context, we need to look at the history of this topic first. Even before I was born during 1980s, people was designing congestion control. It started by the congestion collapse in the internet, of course. But throughout the years, a lot of things have changed, from the technology to the user demand. But at least one thing is not changed, and that is having a lot of different congestion control schemes out there. So the fact that we have a lot of these schemes out there might be a little bit alarming, because if we had a few good ones which can adapt to new demands, we wouldn't have a lot of different designs on a yearly basis. And that is exactly the point. With every new demand and new technology, we saw new waves of congestion control solutions. And that's exactly where learning-based approaches come to the play. These approaches have great potentials to automate the process of searching for better adaptive solutions in this context. Now let's see why using learning-based approaches in the context of congestion control might not be a good idea. To that end, we perform two simple experiments. In the first one, we bring up a network which has about 20 millisecond round trip time and a sender and a receiver. What we do here is we change the capacity of the downlink side in a stepwise manner. And we would like to see how different learning-based schemes operate in this scenario. The key thing is the duration of changes of the capacity is about 500 times more than the minimum round trip time of the system, meaning any congestion control scheme has enough time to converge basically. So we start with two of them, two of the recent learning-based congestion controls. And as you see, they have serious underutilization issue here. And here are the other two. Again, we have issues, but this time serious overutilization issue. I don't have time to go through the details of each of these schemes, but the bottom line here is it seems that using learning-based congestion control goes with serious problems in unseen network scenarios. In the second experiment, we use the same topology, but this time we fix the downlink to about 50 megabits per second. And we send traffic for about 2 minutes. And what we're measuring here is the CPU utilization on the sender side. To have a baseline, I'm showing you here the overhead of TCP cubic, which is the default TCP in most of the platforms, including Linux and Windows. So let's see what happens for the four of the state-of-the-art schemes. Again, problem. But this time it's about the overhead issue. Putting all together, you see a sort of confrontation between the modern approach and the classic approach of doing congestion control here. And it is even highlighted in the motto of the existing learning-based designs. They're trying to have a revolutionary approach, which at the end of the day will replace the old-fashioned congestion control designs. In contrast, what we try to do is this. First, we say we're not interested in the revolutionary approach. We're interested more in a more pragmatic one. Because of that, we're not necessarily replacing any of these schemes. We might be able to collaborate with them. And that is why we have a more evolutionary flavor rather than a revolutionary one. On that note, let me describe the key decision that we made in this work. We start with a two-level control hierarchy. Like before, we do have acknowledgements coming to the sender side, but now we use a more coarse-grained control done by deep reinforcement learning agent to perform periodic actions. And in parallel with that, we use classic heuristics to perform fine-grained control, which is sort of per acknowledgement, as you see. Using this architecture gives us a few good benefits. First is about the overhead. You can imagine that because we're not doing everything by the machine learning part and we have a new partner there, so the overhead of the system becomes lower. The second thing is about performance in unseen scenarios. For instance, in the step scenario that I mentioned, if we use this architecture, we will have this great convergence performance. Now I will describe the details of why it happens in the next slides. So now let's look into more details of the design. Well, let's start with a very brief background on deep reinforcement learning. I will start with an RL setting. In reinforcement learning, we do have an environment and an agent interacting with that environment by performing some actions and observing the changes on the environment through collecting different states and rewards. The key question that an agent tries to answer is what should be my next actions to maximize my future expected rewards from this environment. And as you see, in reinforcement learning setting, we're talking about a sequential learning by considering long-term accumulative rewards. On the other hand, we do have deep neural networks, which are basically nonlinear function transformations. In other words, here we try to approximate a function f, which maps input vector x to output vector y. Deep neural networks are great when we would like to extract representations from raw input signals. And as you see, by combining these together, we will have deep reinforcement learning, which fits very well in our context. Because first, the congestion control is a sequential task. And second, we're not interested in doing handcrafted engineering or basically extracting useful information from different input signals. So now let's look at Orca's design. First, it is congestion control system, and similar to all congestion control systems, the input to the system is acknowledgement packet. And the output is congestion window and pacing rate. And as I already mentioned, we do have two key blocks there, classic heuristic block and learning block, which are glued to each other using a shared memory called socket control buffer. As before, classic heuristic works by using a finite state machine, which determines at different states, you need to do that much of adjustment in the current congestion window of the system. What we have here is we use a monitoring block, which basically collects information from both the network and the classic heuristic by using the socket control buffer. And it generates digestible states for the other entities there. The other block is the reward generation block, which basically looks at the current states of the system and generates a reward associated to that, which quantifies the actions performed by the system. And these inputs go to the agent, and the output of the agent should be a new congestion window, which will be enforced to the socket control buffer. Finally, the output will become the congestion window and the pacing rate of the system through time. So let's see a little bit more details on the agent part. For the reward function, we're trying to motivate the agent toward maximizing the throughput while minimizing the delay and minimizing the loss. That's why we're sort of using this reward that is shown here. And the state of the input, what we use here, we use a more recurrent structure, if you like, which basically means on top of the current state of the network, we add previously observed states also, and then this bundle becomes the current state, goes to the agent. In terms of the algorithm, we use TD3, which is very useful when you have a continuous action space. But there are some key issues and challenges there. The important one is about the huge action space that we have in this problem, plus the real-time nature of the congestion control itself. So we don't have that much of time to sweep the entire space to find good action. That's why we say, okay, so if you don't have time, don't sweep the entire space. But instead, you can use the decision made by the heuristic block as a good guess to start with. And by that, instead of calculating congestion window directly, what we do is we calculate a so-called alpha here, which relates the current congestion window of the system to the one that we are trying to have later. On top of that, as I mentioned, we have two blocks, both of them changing the congestion window. So to smooth out the overall changes, we go with pacing of the traffic, which happened at that rate that I'm showing here. Now let's see how Orca really works in practice. Here I will use two simple scenarios to give you an intuitive idea about its performance. I need to point out that because we have about 70 different inputs, so it's nearly impossible to follow all of them. So analysis here are a very simplified version. In the first scenario, we drop the capacity suddenly through time. We would like to see how the system reacts to this. And as it is clearly shown in these two pictures, what we have is, of course, the delivery rate that we observe comes down, but at the same time, round trip time of the system goes up because, of course, we have queuing delay. And these two will lead to getting lower reward for the entire system. And that means we need to bring down the congestion window. But to see how really system does it, we need to zoom in here. What actually happens is the heuristic block tries to probe for more bandwidth by going upward in terms of having more congestion window. But at the same time, the RL agent learned that it needs to control this behavior of heuristic block. But at the same time, what happens is again the classic approach tries to probe for more bandwidth. This is the time that we have the drop in the capacity of line. And because of that, we're observing lower reward. And this lower reward pushes the agent to basically push down the congestion window size. And this happens again and again. And overall, we will have this downward trend for a congestion window, which basically reduces congestion window in a very short period of time. In the other experiment, what we do is the opposite. We suddenly increase the capacity to see how again system reacts to that. This time you can see that we will have gain suddenly because we have more capacity in the line, but at the same time we don't have any compromise on the delay part. So that means we have higher reward. And this will push the system toward basically increasing the congestion window. But again, if we zoom in, something interesting happens. The heuristic part again tries to, probe for more bandwidths. The DR agent again tries to, control it. But this time, because suddenly capacity of line goes higher, the probing mechanism of the classic TCP helps basically to reveal that we will have higher rewards if we go with higher congestion windows. That's why you see that the DR agent basically increases, the congestion window. And then we will have this upward trend there, which at the end of the day will increase congestion window of the system in a short period of time. So now let's see how we did the training. First, as the underlying heuristic, we use TCP cubic because it is the default TCP most of the platforms, and it gives us a lot of good properties like friendliness and fairness. The second thing is about generation of the environments. We basically chose the cheapest option for now, which is emulating networks instead of going through, real networks. Here, an important thing is we use only simple single button link links, just about 300 of them, as shown in the table. And the overall duration of training is about 6 hours, only 6 hours. And that's another important thing I would like you to remember. Here, now we would like to see how Orca performs during the training. But to give you a better picture, we designed another scheme called clean slate, which is basically achieved by removing the classic block from the system. We would like to see, in addition to the overhead and other benefits that I've already shown you, what would be the advantage of having the classic block there. So this graph shows the overall score that any scheme gets during the training. As you see, the clean slate is able to go up to 20, throughout the training. But Orca can go 3 times more than that and achieve, the score of 60 during the training. And that is exactly another benefit of using the heuristic block there. As I mentioned, we have a real-time system. So that idea that we use helps here a lot even during the training. So now let's look at a subset of evaluations that we've done. As I mentioned earlier, the key objective is to have an adaptive system. And to see how adaptive is Orca, we basically brought up a lot of different network scenarios. For instance, intercontinental class, which includes different servers throughout the globe, or intracontinental servers around the US. And even we went with collecting cellular traces in the city, in New York City, to basically see how different schemes perform in a highly variable link scenario. A very keynote here is we fixed the Orca's training model, which is the output of only 6 hours of training, before doing any of these evaluations. So I'm trying to emphasize on the point that the model is not tailored to any of these, experiments. Now let's look at the overall results that different schemes achieve in different, scenarios. The graphs here are actually showing normalized delay versus normalized throughput on the y-axis. The better scheme is the one who performs at the top right of each graph. The very important thing that I would like you to focus on is how different schemes change their position in different graphs, meaning they might do a good job and be close to the top right of the graph in one scenario, but they will fail, on the other ones. So here we start with the delay-based ones, which are shown here with green color. And I add more. Here we have learning-based schemes, except Orca, of course. And again, you will see this trend that some of them will do a good job in certain scenario, but they will fail in the other ones. Here we do have even cubic and BBR version 2, which happens to follow the same pattern. For instance, BBR version 2 does a good job in intercontinental because it was originally designed for that environment, but it cannot do a good job in cellular traces. And here is the Orca. which is basically performing good in different scenarios. And that was the key. So with only 6 hours of self-training, we're able to achieve consistent high performance in different unseen networks, while others cannot. We do have a few more evaluations that you can check out the paper for them, which represents history friendliness and fairness of Orca and other things also. I would like to conclude with a note here that as Orca's results illustrate, using modern learning-based techniques does not necessarily mean that we need to put aside more than 3 decades of active research in congestion control topic. Thanks for listening.